Chapter 2 in our text focuses more on systems of equations and also different ways we can solve them. Section 2.1 is an introduction into the systems of linear equations. So this is part 1 of section 2.1. So when you have a pair of equations, and we talked about this in the previous section, there are 3 possibilities in terms of what happens with those 2 lines. So when we say systems of linear equations, we're talking about a system of 2 lines and what happens when you have 2 lines. Well, we know that they can cross because that's what happened in the previous section. So they can cross at a single point, and that's what we looked at, in which case you get a single solution. And the terminology that the book uses to describe what happens in this case when they cross at a single point is that it's a consistent, independent system. Consistent because it has an answer. Independent because the x and y are independent based on where they are on the lines. Another possibility is that the 2 lines are actually the same line. So there's one line, and the other line is laying right on top of that line. In this case, you have an infinite number of solutions because every point along the line is a solution. So infinite solution. So again, because it has a solution, the book is going to consider this to be consistent. But this time it's going to be a dependent solution because it depends on what the equation of the line is. So it's an infinite solution. Depending on what x value you pick, you must remain on that line. So it's a dependent system. And the last possibility is what happens if those 2 lines are actually parallel, if they have the same rise and run and they never cross. So they're parallel. Well, in this case, because they do not intersect, there's no solution. This is considered to be an inconsistent system. And they'll never cross. So let's look at an algebraic example of each of these scenarios. How are you going to tell when there's no solution? How are you going to tell when there's an infinite solution? So let's tackle 3 examples that back up each of these. So case 1, let's solve this system. We have x minus 3y is equal to a negative 1, or x plus 3y is equal to 11. You can use either elimination or the substitution method. I tend to use whichever one is the most efficient method. When I look at this one, I notice that just adding them right now, the y's will cancel, so I'm just going to use the elimination method. We'll add, we get 5x is equal to 10, so we know x is 2. We still need the other answer, the y coordinate of the point. So I'll take this x and plug it back into the first equation. So the first equation, which was x minus 3y equals a negative 1, becomes 2 minus 3y equals a negative 1, or negative 3y equals a negative 3, and y is equal to a positive 1. So we get a single solution. We know that because we're getting an answer. So then the solution to this system is an x value of 2 and a y value of 1. And it is a coordinate pair, so you should be writing them as points. We're going to know if it's a no solution or an infinite solution. So let's look at case 2, which was an infinite solution. Case 2 has 5x minus 6y is equal to 8. We also have 10x minus 12y is equal to 16. 5x minus 6y equals 8. 10x minus 12y equals 16. Again, I'll use elimination. It's most efficient for this problem. So let's come in and multiply that top equation by a negative 2. When I do that, I'll get a negative 10x. Oh, let's write it over here. Negative 10x plus 12y is equal to a negative 16. I'm just going to copy the bottom equation the way it is. 10x minus 12y equals 16. Well, what we're going to notice is that everything cancels out. The x cancels, the y cancels, and the constant on the other side cancels. So I get 0 equals 0. This is my clue because it is a true statement. It's true. 0 equals 0. but this is an infinite solution. So anytime I get 0 equals 0, I know it's an infinite solution. The problem is it's dependent. It's dependent upon the line itself. So what our textbook does is it uses the idea of a parameter. So we're going to you can let either variable, let's let y equal t. So t is the parameter. And it's the parameter we're going to write our solution in. So it's just a way of writing the answer in a format where you can pick values for t and then find out where you're at on the line. So if y is equal to t, I'm going to plug that into the top equation, replacing y with the t. So instead of 6y, we have 6t is equal to 8. And now we're going to solve this for x. So 5x is equal to 8 plus 6t, or x is equal to 8 plus 6t divided by 5. So my solution is an x value of 8 plus 6t over 5, comma, t. So now if you pick a value of t, like 1, you can plug it into here and get a value for x, and that's a point that lies on this set of lines, which again are the same line. So that's why it's dependent, because it depends on what you pick for t, and x depends on that value. So, and that's a parameter. We could have used any letter. Your textbook uses a t. Case 3 is our no solution case. Let's take a look at it. How are you going to know when you're solving that that's what has happened, that you have parallel lines? So case 3, our system of equations is 2x minus y is equal to 1. 6x minus 3y is equal to 5. Let's come in and multiply that top equation by a 3. And just a 3 is not going to cancel out the x's or the y's. We're going to need to do a negative 3 in order to have the signs opposite. So let's rewrite them. That will give me a negative 6x plus 3y equals a negative 3. I'll copy the second equation the way it is. 6x minus 3y equals 5. So again, here's the top equation. Here's the bottom equation. Adding them together this time, the x's cancel again. The y's cancel again. So I get 0. But on the other side of the equal sign, the numbers don't cancel and we end up with a 2. So I get 0 equals 2, which is a false statement. So that's how I know it's a no solution. Anytime I get a false statement, it's a no solution. This is simply saying that these two lines have the same rise and run. They're parallel and they'll never cross. That's an example of each of those 3 cases. So on the homework, and what your textbook does in this section is it has us write equations that go along with applications, but not solve them. We actually come back and solve them in a later section. Section 2.3 will come back and solve the equations. Right now, we're just writing the equations. So the directions on the homework and on the handout specifically say, formulate, but do not solve the problem. We will solve these problems in the next section. Clearly define your variables. So example 1, I'll read it and then we'll write down information. Kelly Fisher has a total of $30,000 invested in 2 municipal bonds that have yields of 4% and 5% interest per year. If the interest Kelly receives from the bonds in a year is $1,320, how much does she invest in each of those bonds? So what we know is we're going to invest. We've got a total investment of $30,000. That's our total. We have 2 different interest rates, 4% and then also 5%. And we know that the total interest yield from the 2 investments is $1,320. So the very first thing I always like to do is define my variable. So I'm going to let x be the amount that we're investing at the 4%. Y is going to be the amount that is invested at the 5%. We know together that those 2 investments are the $30,000. So there's our first equation. The second equation brings back into play the interest rates to get our interest off of the investments. So we're going to take 4% times our x, so that's 0.04x. We'll take 5% times the y, so 0.05 y, and that's going to be equal to the 1320, the total interest. So what we're doing is for 1 year, The interest is the principal times the rate times the time, but the time's 1 year, so it disappears from this. And there's our system of equations. So that's all they want you to do. They just want you to write the system of equations. There they are. Okay, example 2 says the total number of passengers riding a city bus during the morning shift is 1,000. If the child's fare is 50 cents and the adult fare is $1.50, the total revenue from the fares in the morning is $1,300. How many children and how many adults rode the bus during the shift? So we know that there were a total of 1,000 people riding the bus during the shift. The child's fares are 50 cents. So child is 0.5 and an adult is $1.50. And we know that the total revenue, so the total amount in money was $1,300. Very similar to the last problem. Again, I'll come in and define those variables first. So X is going to be the number of children who bought tickets. So number of children tickets, child's tickets. Y is going to be the number of adults that rode the bus. So, or the number of tickets. Well, we know together we had 1,000 people. So that would be the X plus the Y is equal to 1,000. Now we're going to bring into it the price per ticket. So if I take the 0.50 and multiply it by the number of tickets that are children, I figure out how much money or revenue I brought in off the children's tickets. We're going to do the same thing with the adult tickets. We're going to multiply them by $1.50. So again, $1.50 times every ticket is how much money you brought in from the adult tickets. Together, these have to equal that $1,300. And there's your system of equations.